Okay, so remember before we get started here, remember that next Thursday, a week from today, is the last day to hand in any missing assignments. That's also the day of your diploma exam. It's Thursday morning here at 8:30. I think the exam starts at 9, but you should be here early for instructions. Okay, so there's a few instructions that we'll be going through before you write your exam. So also we have to clear calculator, so should be here a little bit early. Okay, so this last chapter is on permutations and combinations, and it's different than anything that we've done so far. Okay, there's no transformations in this chapter at all. It's basically the study of counting. How many different ways can things happen? That's really what permutations and combinations are. So an example would be how many different four-digit PIN numbers are available for bank cards. You can determine that using permutations and combinations. How many different possibilities are there? How many different test responses are possible for a test consisting of 10 multiple choice questions, each with 4 possible answers? So if you were guessing at every one, how many different possible answer sheets could you put out? This is another example of using permutations and combinations. Same thing with QR codes. How many different are possible? We can answer that using permutations and combinations. How many different license plates are there? If you can have any 3 letters followed by any 3 digits, and there's no restrictions on which letters or digits you may use. Again, permutations and combinations can be used to answer that question. It talks about restrictions, so we'll be spending time talking about, what happens when there are restrictions. How does that affect the outcome? So we'll be doing that. All right, so again, this is a branch of mathematics actually called combinatorics, and that includes permutations and combinations. It's a branch of discrete mathematics that can be defined as the art of counting. Famous links to combinatorics include Pascal's triangle, which we will talk about, the magic square, the Koenigsberg bridge problem, Kirkman's schoolgirl problem, and the Miriorama cards. So you may have heard of some of these, maybe you didn't, but they're all based on combinatorics. So these Miriorama cards were invented in France and developed further in England. So they were decorated with people, buildings, and scenery that could be laid out in any order to create a variety of landscapes. 124 card set is sold as the endless landscape, and the reason for that is because the number of different permutations or combinations that you can use with some or all of those cards, rearranging the order that they're in, is a very large number. So that's why it's called the endless landscape. And it says, how do you think you could generate, or how long would it take to generate 6.2 times 10 to the 23 possible different arrangements from a 24 card set? So that is the number. That's how many different possibilities there could be for rearranging those 24 cards amongst themselves. 6.2 times 10 to the 23rd, that's 6, 2, and then 22 zeros after that. Big number. So we're going to see where this comes from. All right. So let's dig into this. You just want a trip to San Diego for the weekend, but you can only take a carry-on. So you pack 3 t-shirts, a black, a gray, and a white, 2 pairs of socks, or shorts, a red and a white, and 2 pairs of sandals, 1 gray, 1 black. How many different outfits are possible? Okay, so you might think, guess, whatever. How many different possible outcomes this person could wear on this trip? And we're going to see that there's different ways that we can calculate the actual answer. So you might have a number in your head, what you think the answer is. Let's see if you're right or not. One way to do this is by using what's known as a tree diagram. So we'll start with the t-shirts. There's black, gray, and white. So as I set this up, I'll put t-shirts at the top here. And below that, I'll put my different colors. Black, gray, and white. Now, for every t-shirt that the person selects, they have to choose from two shorts. So if our next column is the shorts, and for every t-shirt they choose, they can choose a pair of shorts that is either red or white. So for each t-shirt, they can choose shorts that are either red or white. For each t-shirt. And then they still have to choose a pair of sandals. And they have two choices for their sandals. And those are black or gray. So I'm just going to put B for black, G for gray. So for every pair of shorts they choose, they have two options for sandals, either black or gray. And so you can follow along and use this called a tree diagram. It's basically, it's like you have branches here, right? So one choice would be choosing a black t-shirt with red shorts and black sandals. That's one possible outfit that this person could choose. Or they could have a black t-shirt with red shorts and green sandals, and so on. So basically, if we count up all the B's and G's we have in this last set of branches, that'll be the number of possible outcomes that this person could choose from. So it's 2, 4, 6, 8, 10, 12. There are 12 different outfits that this person could choose. The other thing that's important to realize is that the order that the items are chosen do not affect the final result. And so that's one thing that we will be talking about. Does order matter or not? Because if it does, we do it a slightly different way than if it doesn't. So it's something that we're always going to be asking ourselves. Does order matter or not? So the tree diagram works. Takes a bit of time and a bit of room, but it works. But there is another way without listing all the possibilities or drawing a tree diagram. And if you think about it, there were 3 choices for t-shirts. There were 2 choices for shorts. And there were 2 choices for the sandals. The question is, what could you do to those 3 numbers so that you get the answer of 12? Multiply them. That's right. If you take the number of choices for the t-shirts times the number of choices for the shorts times the number of choices for the sandals, you get that number 12. So this is a strategy that we would use if we just need to know the number of different possibilities there are, as opposed to what are the different possibilities. Because the tree diagram would be used for what are the different possibilities. You can also obviously use it for how many are possible, but if that's all you want, then this second method would be the way to do it. Multiplying those together. And we have a name for that. It's called the fundamental counting principle. If one task can be performed in A ways and the second task in B ways, then the 2 tasks can be performed in A times B ways. For example, a restaurant meal consists of one of 2 salad options, 3 entrees, 4 desserts. So the number of possible meals there, if you choose one from each category, would be 2 times 3 times 4, or 24 different meals are possible. So let's look at some examples using this fundamental counting principle. A Math 30-2 quiz consists of 8 multiple choice questions. Each question has 4 choices. How many different sets of answers are possible? So as we go through these, we're going to see many times we're going to put down spaces. I'm going to put down 8 spaces here because there are 8 questions on this test. And every question has 4 possible answers to choose from. If you are guessing, there's 4 possible answers for the first question, 4 for the second, and so on. And remember, the fundamental counting principle says that these numbers are multiplied together. Essentially, it's just 4 to the power 8. 4 is multiplied by itself 8 times, and so we can do that on our calculator. And we'll get 65,536. So there's the answer. If you were to guess at every question, this is how many different possible answer sheets you could come up with. Big number. An online game has asked you to create a password. It must consist of 4 characters in length. It must be 4 characters in length, and you can use any lowercase letters, any uppercase letters, and any digits to create your password. So there are 26 letters in the alphabet. So you have 26 lowercase plus 26 uppercase. There are 10 digits, 0 through 9. So that gives us a possible or total number of 62 letters or characters, I guess, that we can choose from each time we choose. So part A asks, how many passwords are possible if you may repeat any character? So it's going to have 4 characters long, and if you are allowed to repeat any character, there's no restrictions. That means you'd have 62 choices for each one. So it's 62 multiplied by itself 4 times, or 62 to the power 4 would give us the answer. Big number. 14,776,336. Then part B wants to know how many passwords are possible if you are not permitted to repeat any character. So you still have 4 characters to choose from, and you'll have 62 choices for the first one, but you can not have any repetition. So after you've chosen one for the first, it can't be used for the second one. So now there's only 61 choices for the second character, and then 60, and then 59. So for this, we'd have to multiply out the 3 numbers. Still a big number, 13,388,280. But obviously, when you have those restrictions, you have less options. The total number is going to be less. So it's about 1.5 million less compared to what we got for part A. So these are types of questions that are common to see on a diploma exam. Something basic like this, that we're just using the fundamental counting principle. Example 3 says, determine the number of distinguishable 4-letter arrangements that can be formed from the letters in the word English, if there are no restrictions, which means you're going to use all the letters and there's no restrictions on where certain letters can be. But this word has 7 letters in it, so if we mark down 7 spaces, actually, I'm sorry, it's 4-letter arrangements out of all 7. We're only using 4 of the 7. So that means you'd have 7 choices for the first letter, and then 6, and then 5, and then 4. Like you're arranging the letters, so once you choose a letter and write it down, it can't be used again. Because you're actually arranging them, you're writing them down. And so if we multiply those numbers together, 7 times 6 times 5 times 4, that gives us 840. So there was a restriction here, and that is that you're not using all the letters. You're only using 4 of the 7. Part B is a different restriction. The first letter must be the letter E, which means there's only one choice for that first letter. So we've used one letter already. We started with 7. Now we have 6 left for the next one, and then 5, and then 4. So I think that's 120 when you multiply those out. But in this case, your restriction is that the first letter must be an E as well. You're only using 4 of the 7 letters. Part C says that the arrangement must contain the letter H. I'm going to grab this booklet. So there are 4 different scenarios that we have to look at here. The first being that if the first letter is an H, it just says that the arrangement must contain the letter H. So it could be in the first position, it could be in the second position, the third, or the fourth. So that's what those ones represent. There's one choice for each of those, and that's putting the H in that specific spot. Again, the question says the arrangement must contain the letter H, but it doesn't say where. In part B, it told us that the first letter must be E. So there's only one way that can happen. But for the arrangements to contain the letter H, there's actually 4 ways that can happen. It can be in any one of those 4 positions. The rest of the numbers will look the same as part B. You started with 7, you've used 1, so now there'll be 6, then 5, then 4. So that is 120. 1 times 6 times 5 times 4. And we're going to get the same number for the rest of these possibilities. If the H is in the second position, again, you started with 7, you've used 1. Now you have 6 left for the first position, 5 for the third, and 4 for the last. Again, that gives us 120. You're going to get 120 from all of these. You're multiplying the same numbers together. And so basically it's 120 4 different times, which is 480. So there's the answer. So you see the difference between specifying what position a letter must be as opposed to saying that the arrangement must just contain that letter. Part D says the first and the last letters must be vowels. So you've got 4 letters, 4 characters you're going to choose. If we look at the letters of the word English, there's actually only 2 vowels there, the E and the I, which means you'd have 2 choices for the first letter, 1 choice for the last letter. It must begin and end with a vowel. There's only 2 choices for the first position because the only 2 vowels you have are the letters E and I. And once you've chosen, it can't be chosen again. We started with 7. We've used 2 up already. That means you have 5 and then 4 left for the remaining choices. So that gives us an answer of 40 different possible arrangements of those characters. Number 4, how many ways can a teacher seat 4 girls and 3 boys in a row of 7 seats if a boy must be seated at the end of each row? So you have 7 students and you're arranging all of them. There are 4 girls and 3 boys, which means you'd have 3 choices for the first position and then 2 choices for the last. It says that a boy must be seated at the end of each row. There's 3 boys to begin with, So you'd have 3 choices for the first position and 2 for the last. Now, if you switch those 2 numbers around, it doesn't change it. Right? When you multiply numbers together, order doesn't matter. So you could put the 2 in the first position and the 3 in the last. Doesn't matter. But we started with 7 students. We've used 2 of them up already. So that means we'd have 5 for the next, and then 4, 3, 2, and then 1. So it's 3 times 5 times 4 times 3 times 2. And you can multiply by 1 if you want. That doesn't change anything. But then the last digit is a 2 that you're multiplying by. So that gives us 720 different arrangements are possible. How many 5-digit numbers can you make using those digits if repetition of the digits is allowed? So you've got 5 digits to choose from, and you're going to arrange all 5 of them. And repetition is allowed, which means you'd have 5 choices for each. So that is the same thing as 5 to the power 5, which is 3125. So obviously, as you're doing these, you need to look and see if there's any restrictions. Is repetition allowed or not? If we say then that repetition is not allowed, will this change the answer? Absolutely it will, because now you're going to have 1 fewer choice each time. After you've picked the digit, it can't be selected again. So it's 5 times 4 times 3 times 2. And again, you can multiply by 1 if you want to, but you don't need to, because timesing by 1 changes nothing. So there's quite a bit fewer choices or possibilities when you put that restriction in there. So we multiplied 5 times 4 times 3 times 2 times 1. In math, we can denote that as 5 with the exclamation mark at the end. And that symbol in this application means factorial. So 5 times 4 times 3 times 2 times 1 is 5 factorial. And there's a factorial key on your calculator. So if you go math first, 5 first to put the 5 in there, and then math over to probability, and number 4 in that list is factorial. So math over to probability, and number 4 in that list is factorial. So if I just hit 4, the factorial key is there, and your calculator does that. It multiplies 5 times 4 times 3 times 2 times 1. So that's definitely a shortcut that we can use. So in general, n factorial is n times n minus 1 times n minus 2, and you keep going until you get down to times 3 times 2 times 1. And 0 factorial is 1. If you try it on your calculator, math over to probability, number 4 is factorial, it'll tell you that 0 factorial is 1. And we're going to see why in a little bit here. That is true. But anything 0 factorial is always 1. So the arrangements of objects or people in a line is called a linear permutation. In a permutation, the order of the objects is important. When objects are distinguishable from one another, a new order of objects creates a new permutation. So that's what we need to remember, is that if order matters, it is a permutation. As opposed to a combination, which we'll look at tomorrow, that's where order doesn't matter. So I'll give you an example, a simple example. For your grad class, let's say that you have elections, which you did. You nominated or elected a president, a vice president, a secretary, and a treasurer, let's say. Well, the order that those people are chosen matters. One person's a president, one's a vice president, etc. But if you just say you're selecting 4 students to sit on a committee and they all have the same job, then order doesn't matter. That would be an example of a combination because the order that they're selected doesn't matter. So something we're always going to be asking ourselves as we go through this, does order matter or not? If order matters, it's a permutation. That's an ordered arrangement or sequence of all or part of a set. So as a lead into permutations, let's evaluate these without using a calculator. So 10 factorial, without using a calculator, here's how this looks like. It's 10 times 9 times, and we can keep going all the way down to 1. However, because the bottom is 8 factorial, that's where I'm going to stop at the top. 10 times 9 times 8 factorial is the same as 10 factorial. But the reason I stopped at 8 factorial is because that's what the bottom is, and I can cancel them. I can divide top and bottom by 8 factorial, so you're just left with 10 times 9, which is 90. That's the value of that, which we can check on our calculator. 10 factorial divided by 8 factorial. Gives us the same answer, 90. So same thing with question B, 7 factorial over 4 factorial. 7 factorial is 7 times 6 times 5, and we can keep going down to 1, but I'm going to stop at 4 and put a factorial on it. That's the same thing as what's above. However, by doing this, we can cancel the 4 factorials. And you're left with 7 times 6, which is 42, times 5, which is 210. So that would be the answer. Which again, we could check by doing the original question in our calculator. Right? There have been questions like example 7 on the diploma exam before, where you're simplifying an expression involving a variable. So like we did above, you need to expand one of them so that you'll get some canceling happening. And you always want to expand the larger number or the greatest expression. So for all values of n is greater than n minus 3, which means that you're going to expand n factorial. That is the same as n times n minus 1, and we can keep going as long as we want, but I'm going to stop at the n minus 3 and put a factorial on the end of that. Just like above, whenever you expand, the last number, or in this case, the last factor, has a factorial on the end. And the reason I stopped at n minus 3 is because the denominator is n minus 3 factorial. So now we can divide both top and bottom by n minus 3 factorial. They cancel, and you're left with n bracket, n minus 1 bracket, n minus 2. So there's the simplified expression. So again, when we're doing these, we always expand the larger of the two expressions. For question B, n plus 4 is greater than n plus 2. So we're going to expand the n plus 4 factorial. So the first term is n plus 4. The next term is 1 less, n plus 3. The next term is 1 less, which is n plus 2. I'm going to stop there and put a factorial on the end because that's what the denominator is, n plus 2 factorial. So now they will cancel, and we're left with n plus 4, n plus 3. So there's a simplified expression. There's also been questions on diploma exams where you have to solve an equation involving factorial. And the first step will be doing what we just finished doing, and that is simplifying. N plus 2 is greater than n plus 1, so we're going to expand the n plus 2 factorial. So the first term would be n plus 2, the next one would be 1 less, which is n plus 1. I'm going to stop there and put a factorial on the end because that's what the denominator is. So the n plus 1 factorials cancel. You're left with n plus 2 equals 6. So n equals 4. And we could definitely check this if we wanted to. If you let n equal 4 in the original question, you'll have 4 plus 2 factorial on top, or 6 factorial. Divided by, again, when n is 4, the bottom is 4 plus 1, or 5 factorial. And that does equal 6. So we can check that. Okay, we're going to continue on doing part 2 of permutations. So we saw that the number of permutations of n different objects taken all at a time was n factorial. So looking at a few more examples, how many permutations are there of the letters in the word? So again, as soon as you see permutations, that mean order matters, and we can use the fundamental counting principle or factorial to get our answer. We're going to arrange all of the letters in these words. So the first word, Regina, has 6 letters. They could be arranged in 6 factorial ways. And 6 factorial is 720. So you definitely could put down 6 spaces if you wanted. Maybe 6 choices for the first letter, then 5, then 4, then 3, and so on. But now we know what factorial means. We can just go straight to that. The word Kelowna has 7 letters in it, so that would be 7 factorial ways. I could take the previous answer of 6 factorial or 720 and multiply it by 7 if I wanted to, because 7 times 6 factorial is 7 factorial. Or you could just do 7 factorial on your calculator. You'll get the same answer. Example 2, how many ways can 8 children line up at a water fountain? Well, that would be 8 factorial ways, which we could get by taking the last number and multiply by 8. 7 factorial times 8 is the same thing as 8 factorial. Or if you did 8 factorial, you get the same answer, 40,320. As we've seen, though, sometimes we're not always arranging the entire set of objects. For example, if there are 7 members on the student council, in how many ways could the council select 3 students to be chair, secretary, and treasurer of the council? Using the fundamental counting principle, that would be 7 times 6 times 5, which is 210. Using factorial notation, though, we could say that we can get that same answer, 7 times 6 times 5, by going 7 factorial over 4 factorial. We get the same answer, 210, as shown in this example. The question is, though, where does that number 4 come from? Well, if we read on, the notation NPR is used to represent the number of permutations or arrangements in a definite order of R items taken from a set of N distinct items. The formula for NPR is it's N factorial over N minus R factorial. That's where that 4 comes from. In the example above, we were arranging 3 objects from 7. So that would be 7P3. Arranging 3 objects from 7, and order matters. And according to the formula that we see below, that is 7 factorial over 7 minus 3 factorial, or 7 factorial over 4 factorial. So that's where that 4 came from. It's the difference between N and R. The formula tells us that's where we get our denominator. So there is also an NPR function on your calculator. It's in the same place as factorial is, but you have to put the 7 in first. So 7 and then math over the probability. You see number 2 in this list is NPR. So 7P3. Older operating systems won't actually show the 7 and the 3 as subscript. Older operating systems, after you put the 7 and then you choose NPR, it'll actually say NPR. And then you put your 3 in after and hit enter, and it'll give you the same answer. So this is what we can use when we're not using all of the objects for an arrangement, only some of them. So I said we'll define what 0 factorial is. If we replace r by n in that formula, right? The formula was NPR equals, NPR equals n factorial over n minus r factorial. Well, if we replace the r with n, then you're going to have npn. And that would be n factorial over n minus n factorial using the NPR formula, or n factorial over 0 factorial. However, NPN is what we really was doing when we started this whole talk about fundamental counting principle. If you have 5 letters in a word and you're arranging all 5 of them, we saw that was 5 factorial. That's the same as 5p5. You're arranging all 5 of the objects. So NPN is the same thing as n factorial. These two expressions are equal to each other. And so because of that, the denominator must be 1. And that is why 0 factorial equals 1. The two top expressions are the same, so the bottom expressions have to be equal as well. So this is the reason why 0 factorial equals 1. So you'll never be tested on that. You might be asked, though, to give a proof of why 0 factorial equals 1, and I just showed you what that proof would look like. So let's use this shortcut, the NPR, to answer these questions. In a South American country, vehicle license plates consist of any 2 different letters followed by 4 different digits. How many different license plates are possible? First, using the fundamental counting principle. So you'd have to do this in 2 parts. One for the different letters and the other for the different digits. There are 26 letters in the alphabet. So you would have 26 choices for the first character. And if you read what it says above, it says 2 different letters. So that means no repetition. So there'd be only 25 choices for the second letter. There are 10 digits to choose from, 0 through 9, but again, they must be different. So after 1 digit is chosen, it can't be chosen again. So using the fundamental counting principle, we'd have to multiply all 5 numbers together. 26 times 25 times. Gives us an answer of 3,276,000. Now, what if you wanted to use permutations to do this? Again, you'd have to do 2 different cases. The first would be choosing the letters. You're choosing 2 letters from 26. So that would be 26P2. You should also realize that when you're using permutations, it means that repetition is not allowed. Okay? If repetition is allowed, you must use the fundamental counting principle. The fact that we're using permutations here in this scenario where repetition is not allowed tells us that You can use permutations NPR as long as repetition is not allowed. If repetition is allowed, you must use the fundamental counting principle. So there's a number of ways of getting your letters times. There are 10 different digits to choose from, and you're going to choose 4. And again, order matters. So that would be 10p4. So we can do this in our calculator, all in one step. So I've got 26p2 times 10p4. You get exactly the same answer. So in many cases, you'll have the choice, the option of doing fundamental counting principle or permutations. Depending on how many numbers there are that are being multiplied together, in many cases, permutations will be a quicker way to do it, but they'll both work. All right, looking at number 4, consider the letters in the word formula. So something else I want to point out right now is in every case, all of the words that we've dealt with have all had different letters. The next thing we're going to look at is what happens when there are things that repeat. There's lots of words that have more than one letter of the same. The word feeling has 2 E's, for example, right? So how do you deal with that? Well, we're going to get to that. But right now, all the letters have no repetition, or all the words have no repetition of letters. So example 4, consider the word formula that has 7 letters. How many different arrangements are there using all the letters? Well, that'll just be 7 factorial. Or you can go 7p7. They're the same thing. Doesn't matter. I'll just use factorial, and we get 5040. Part B says, what about only using 3 of the letters? So now we will use permutation 7p3, which we can do in our calculator. If you use the formula, it would be 7 factorial over 7 minus 3 factorial, or 7 factorial over 4 factorial. But we don't even need to do that. You can just use the permutation function of our calculator to do 7p3. But if we did 7 factorial over 4 factorial, it'll be the same. No matter which way you do it. Number 5 says use the formula to evaluate that. So 9p4 would be 9 factorial over 9 minus 4 factorial, or 9 factorial over 5 factorial. We could simplify this. 9 factorial means 9 times 8 times 7 times 6. And we could keep going, but we would stop at 5 and put a factorial on the end because that's what we have on the bottom. 5 factorial. They cancel. And you're left with 9 times 8 times 7 times 6. $3,024. Which you could definitely check that by doing 9p4. You get the same answer. But we're going to see right away here that there are some times when you must use the factorial or the formula, because we're going to see some on the next page where there's some of these where there's letters involved, not just numbers. So example 6 says, show that 100 plus 99 factorial is equivalent to 101 times 99 factorial without using technology. Here's how this works. It's actually not too bad. Once we go through it, you'll see. 100 factorial plus 99 factorial. Well, 100 factorial will be 100 times 99, and we can keep going as far as we want it, but I'm going to stop at 99 and put a factorial on the end. And the reason for that is because our second term is also 99 factorial. So again, this portion here is the same thing as 100 factorial. Start with 100, your next number that you're multiplying by is 1 less, and you can keep going forever. Well, not forever, until you get down to 1 if you want, or you can stop anywhere you want as long as you put a factorial on the end of that last number. So that's equivalent to just 100 factorial. But now I have two terms here, and there's a common factor of 99 factorial that I can take out from that expression. To get what's inside the brackets, you divide each term by 99 factorial. So when you divide 100 times 99 factorial by 99 factorial, you're left with the 100. Plus, when you divide 99 factorial by itself, you'll get 1. And 100 plus 1 is 101. And that's the same thing as 101 times 99 factorial. So we've just shown that those two expressions are equivalent. Okay, number 7. You're asked to solve these. Now, you could do it with guess and check, but if you see a question like this on a test or on the diploma exam, it's going to say determine, or algebraically determine, or algebraically solve. So you got to show your work. You could definitely use your calculator to check, but you need to show where you're getting your answer from, and that would be using the formula NP2. Using the NPR formula, that'll be n factorial over n minus 2 factorial equals 20. And like we did before, we're going to simplify. We have to decide if we're going to expand the top or the bottom so that something will cancel. And we said that we always expand the larger of the two expressions. N is greater than n minus 2. So we're going to expand n factorial. So the first factor will be n. The next one will be 1 less, n minus 1. The next one will be 1 less again. And we could go on for as far as we want, but we're going to stop at the n minus 2 and put a factorial on the end because that's what the denominator is. And like we've seen before, the n minus 2 factorials will cancel. And so now we're going to solve this equation that we have left here. If you multiply the n and the n minus 1 out, you'll get n squared minus n equals 20. So we have this quadratic to solve, and you might remember to solve quadratics, we always make them equal to 0, and then we see if we can factor them. And this one can be factored. It'll be n minus 5, n plus 4. So our solutions will come when each factor equals 0. Which will give us two answers, but remember that n refers to the number of items you're choosing from. It cannot be negative. N is the number of items you're choosing from. That's an extraneous answer. So our only answer should be that n equals 5. And we can check that by going 5p2 in our calculator to make sure we get 20 as the answer. So 5p2 does equal 20, so we know our answer is correct. Okay? Question B, I would start this by first dividing both sides by 2. Get the NP3 by itself. And using the NPR formula, NP3 is n factorial over n minus 3 factorial. We're going to simplify by expanding the larger of the two expressions. N is greater than n minus 3. So after the n, the next factor is 1 less, which would be n minus 1, then n minus 2, and then I would stop after the n minus 3 and put a factorial on the end. because that's what the denominator is, n minus 3 factorial. So the n minus 3 factorials cancel. And in this case, you got n times n minus 1 times n minus 2. If you multiply all that out, you will get n cubed minus 3n squared plus 2n if you multiply those out. So you get a third degree polynomial here that we want to solve. But before we solve it, we need to make it equal to 0. And in a case like this, like we now need to factor this, right? And so remember, we can use our graphing calculator to help us find out what the first factor is by finding an x-intercept of this graph, of that equation. So we use our graphing calculator to find that. X to the power 3 minus 3x squared plus 2x minus 60. Zoom 6 to set our windows to their standard settings. Looks like we have an x-intercept at 5. Let's just check that. Go into the trace mode, let x equal 5. Yes, y does equal 0 there. So positive 5 is an x-intercept, which means x minus 5 must be a factor. Or in this case, we change it to n minus 5. But what we always did is we change it to a plus 5 instead of a minus 5, so we could add as we go along here. We're trying to find any and all answers for n here. That'll make that third degree polynomial equal 0. So 1 times 5 is plus 5, and we're adding. 5 times 2 is plus 10, and we're adding. 5 times 12 is plus 60. We get a remainder of 0. So this gives us our first two factors. N minus 5 is one factor. Our other factor will be n squared plus 2n plus 12, which cannot be factored. It cannot be factored, which tells us that our only answer is n equals 5. It's where n minus 5 equals 0, so n equals 5. Which, again, we can check going back to the original equation. So 2 times 5p3 should be 120, and it is. So it checks. Our answer works. All right. So tomorrow we'll start looking at some questions where there's more restrictions or where we have letters that are repeating, and how do we handle that. So what you should work on is, if you back up a few pages, you'll see that assignment number 1. So that's page 9 and 10. You should work on those questions. And then on top of that, for practice what we did in lesson 2, should also do some of these questions. Page 524 to 525. Questions 1, 2, 4, 6, and 7. I will post these to Google Classroom so you can check your answers. Again, it'd be a really good idea to do the practice. Okay? Pardon me? Yep.